So, hello everybody. Welcome to the second meeting of this semester. This meeting is going to be on the world of programming languages, and joining us joining us this time is Alana.
Hello.
She'll be leading this presentation, and I hope everyone enjoys.
Cool. Hesitant clapping fills
You
the
get
room.
3 claps for now.
This is gonna go great. Alright, I'm gonna switch this for the recording.
Hey, bruh.
This is why Rob wanted to use his computer.
What's going on
I did.
here?
That's why Rob really wanted to use his computer. Is it supposed to be reversed? Anyway.
Oh yeah, it's only that. It's only.
Oh, it's only on this end?
Yeah.
Okay, cool. Got a little worried there for a second. Yeah, I'm gonna lose my cursor so many times. Okay. So, first off, like Rob said, my name is Alana. I'm the keeper of the lore. My title has changed. So I had to think about it. And I'm also in my final year as a computer science major here at UMBC. We kind of bamboozled you all a little bit. In like all the announcements up to this, we kept saying functional programming. That was not the entire truth. So the thing that we realized was that we can't really talk about functional programming without talking about the other paradigms and comparing them, but then you also have to know how they work and why they are different from this and blah blah blah. So we're just gonna do all of them. Well, not all of them. We're gonna do like a group of them, and we're also gonna talk about the differences between how other types of categories that programming languages can fall into. Hence, world of programming languages. Yay! Okay. So let's get started, because we did start today late. Okay, cool. Dang it. Okay, cool. Well, anyway, so I don't like your computer. So, so first off, what is a programming language? If you're new to programming, you may not be like, what the heck really are they? So essentially, humans speak one sort of language, and computers speak a very different language, and they can't talk to each other directly. It's kind of hard to do so. So programming languages essentially act as a happy little medium to allow us to tell the computer what to do, and sort of like vice versa a little bit. So, and there are a lot of different programming languages out there. I actually looked this up. There's like 2,000. There are a lot of them, and a lot of them were made with specific use cases in mind, like database management or AI or data science, stuff like that. And there are a lot of ways to describe these programming languages. Why? I haven't the foggiest idea. I don't know why. It does make sense, like, to want to try with so many to just sort of like say, hey, these are these buzzwords that sort of give you an idea of what the language is, but even then, that's kind of misleading. So the first way, I told you I was going to do this. There we go. So the first thing I did was look up what are the different categories of programming languages, and a quick look at this Google feed will show you that I had a problem. I was not going to have a fun time with this, because as you can see, it's kind of hard, but it'll be like 5 major types, 3 types, 5 basic programming languages, 6 types of programming languages. One of those links says 50 types of programming languages. 50. Yeah, this presentation has gone through a lot of restructuring because of this problem. Because people can't seem to decide what the main categories of programming languages are, and just what constitutes as its own category versus what's actually a subcategory versus this versus that versus all this fun stuff. So this made things very hard. This is what it felt like when I was trying to piece together this freaking presentation and figure out how's the best way I could explain this. So this presentation is just going to end up being the brainchild of how I've seen things be laid out in terms of how to describe a programming language. So first off, from what I found, there's like 2 main ways to describe a programming language. The first is how it's worked, or the structure, the properties that language has, and the second is just how it runs on the machine. So we're going to start with the first category of the structure and the properties of the language itself. So first, you'll find your declarative languages. What's a declarative language, you may say? Well, declarative languages are essentially languages where you tell the program what to do, not necessarily how to do it. Think of it sort of like SQL. You don't tell SQL how to retrieve something from a database. You just say retrieve this, and then from there the computer sort of decides what to do. So that's, like I said, it's up to the computer. You don't decide the control flow. You don't say do it like this, really. And it can be, because of that, it's sort of easier to read these languages sometimes. Not really if you're not really used to it, but it is overall easier to read these languages, and they tend to be more concise, fairly shorter, because that extra step of saying how to do it isn't there. The subcategory of one of the subcategories of declarative languages is logic programming languages. They are based on formal logic, which is the study of logical truths, things that are supposed to be true. And it's kind of hard for me to see the slide over there, so I have to scroll up my presentation, which doesn't sync. Okay, there it is. So it's based on things that are true no matter what. So essentially, you tell the programming languages a bunch of facts and rules about the problem you want to solve, and then you give it a prompt, or you give it the problem, and based on those rules and facts, it'll try to make assumptions and inferences and get to a conclusion. An example of these programming languages is, and I flipped it again, is Prolog. Nicola, this is for you. So Prolog first appeared around 1972, and it was invented to be mainly declarative. It wasn't really made for anything else beside that. What's he saying?
Yeah.
So it works like I sort of explained it. You state the clauses and facts, you send in a query, and then it'll go through that knowledge base you gave it and come to a solution. And it's most commonly associated with AI. CMSC 471, Intro to Artificial Intelligence here at UMBC, actually does cover Prolog if you take it with Dr. Finan.
331 did as well.
331 did as well, right, I forgot about that. So yeah, there's the logo for Prolog, he's pretty cute. Yeah. I don't know how well these memes show up on the screens. But yeah, okay. My cursor keeps running around because I keep losing track of it. It shows up great? Fabulous. So here's an example of Prolog. So before I get into showing the coding samples, essentially the way this presentation is going to structure is that I'm going to explain a type of a language, I'm going to explain an example, and then I'm going to show screenshots so that way you guys can compare the different languages. So the only way to get that fair baseline is to write the same program in all these different languages. And the reason the program I chose to show was to calculate the factorial of 5. So 1 times 2 times 3 times 4 times 5, output the result.
Nicola's a fan.
Nicola's a fan?
He likes the example.
Fabulous. Okay. So, and I'll explain why I did that instead of something simpler in a bit. But, so there is the code for calculating the factorial in Prolog. I don't like it. It took a while for me to find that. That's not actually originally mine. I actually had to look at, I think, 2 different sources and combine them together because the individual sources did not work. So that's what calculating the factorial looks like, and this is how you would run it on, I'm using Debian. So you would launch the script in SWPL, don't know what that means, SWIPL I think it is. And then you just say the name of the script, it's going to load up the knowledge base, and then you type in the clause, so factorial, and then the number, which is case 5, is going to print out 120, and it's going to print out true, which is saying that it reached a conclusion, it found an answer that it deemed correct. But yeah, that's how you would calculate the factorial in Prolog. Isn't it great, guys?
I don't understand this at all. That's
okay. That's okay.
Is this what goes on in Nicola's brain?
I don't know, Nicola, can you? Hell yeah. Okay.
I feel sorry for him.
Deep dive.
Dive into Nicola's subconscious. Anyway.
Nicola's subconscious.
The next type of languages are query languages. Query languages are kind of what they sound. They're languages specifically made to retrieve data and manipulate database systems. So that's not just like your SQL databases. That's also, there's, Patrick, I know you're in this chat. Something called Sparkle. It's like this whole thing about making the web smarter, all that fun stuff. I'm not going to dive into that, but essentially that they have their own special type of databases, and Sparkle is like their query language for that. So here's my meme for query languages. Yeah, I got very distressed during this presentation, so I put a lot of memes in here to make me happy. But also, one thing I learned in this presentation, there are a lot of query languages.
Oh my god.
Like, if you thought there were a lot of derivatives of SQL, guess what? There's more that may not be SQL. I know some of them definitely aren't. It's strange. It's scary. We're gonna move past the scary now.
There's a bunch that just have QL at the end.
Yeah. Query language. QL.
Oh, okay, fair enough. I'm sorry.
You're-
I was
you're
thinking
gonna
like,
hear-
oh yeah, copy S.
Excel is
Yeah, I know this
language.
one.
It's unlike SQL, it's Turing complete.
That's Patrick, right?
Yeah.
Okay. So,
Patrick is definitely
like I said earlier, an example of a query language is SQL. It was initially developed in 1973 to actually by IBM to query their databases, and eventually it became more of a standard for just databases in general. Years later, it stands for the Structured Query Language, and like as stated there, it's the main language used for relational database management. If you take databases here at UMBC, that is the language that they will use. Duh. And I think that's all I had to say on that. There's my meme. Don't show this meme to Dr. Kalfakis, he'll get mad at you.
You know this by experience.
I know this by people telling me. I have not tried yet, but he did go on a bit of a rant in class once about file databases. Anyway. There are a lot of derivatives of SQL. I think everything in that meme is based on just straight up regular SQL. I use SQLite for this just because it meant I didn't have to set up a SQL server. It's just a database file. It's pretty great.
Use Docker though.
So here's an example of SQL. I'm gonna be real. I didn't feel like wanting to calculate how to do a factorial in SQL. So instead, I just made a table with 5 and then its factorial, and then I just retrieved it using a SQL query. It gets the point across. You didn't tell SQL how to retrieve the data, you just told it what data to retrieve, and it retrieved it. Yay, I didn't cheat. It's fine, guys. It's fine.
Select factorial with your table 1.
Yeah, exactly. See, it's fine. Everything's fine.
It's built right in.
So next, which was the topic that originally started everything, was functional languages. What the heck are these? Well, there's languages solely based on functions, and they're also heavily based in math. That's not on this slide because it got a bit complicated with that, but these languages tend to be fairly heavily based in math. But their functions are usually called pure functions, which essentially you give it an input, it gives an output, and every time you give that input, it will always give the same output no matter what. And the reason for this is because these functions have no side effects. They don't modify arguments, they don't modify any local or global variables, and they don't modify any I/O streams. So anything you give it, it'll always give it out no matter what. And no looping. There are no loops in purely functional language. If you want to loop, you have to use recursion, hence the XKCD comment. And variables are also immutable. You really can't change them once you make them. If you want to change the value, you kind of have to assign it to a new variable. But again, these are all in purely functional languages. You can have a lot of languages that have functional structures or aspects of it, but aren't functional in themselves. And that's why I was saying earlier that things can be confusing when you try to categorize programming languages because everything blends together so much. And yeah, functions in functional languages are also first-class objects, which means you can assign a function to a variable, you can pass a function in a parameter of another function, and you can return a function as a return value in another function. It's great. And there's also lazy evaluation. So variables tend to only be evaluated and stored if they are needed. So if I have a function that my program doesn't use, it's not going to do any of that with that function. It's only going to do that with the functions that we use. An example of this one is Haskell, first developed around 1987. It is purely functional, as I said, so everything that I said in the previous slide holds for Haskell in most of its entirety. And it's also compiled. It is a compiled language. The compiler is GHC. It has garbage collection because, again, all the variables are immutable. That causes problems if you don't get rid of it all. And it's also statically typed, meaning that, well, it's optionally statically typed. Statically typed means you have to specify if something is an integer or a boolean or a string or something like that. And it's used a lot for server-side applications and even the creation of other compilers for other languages. It's kind of nuts. So here's my coding example for Haskell. This was not written by me because I was running out of time for this presentation and stressed. So my friend Drew wrote it for me, who really likes Haskell and wanted to refresh up on it. So here's how you calculate factorial in Haskell. I'm seeing a lot of snickers. What's happening in the chat?
We got a sweaty.
What?
We also got a base, unlike JavaScript, a poster child of dynamic typing. Recursion.
But as you can see, you have to use recursion to calculate the factorial in Haskell because you can't loop. And that's how you, and I didn't show it on this one yet.
No
Ah.
branching either?
Huh?
No branching either?
No, there's an if-else statement in there.
You don't know
No. I didn't write this. I don't think there is. Because you because you don't control like the steps it takes, the program decides it. So either I don't think there would be go-tos. I wouldn't be surprised if there are. But that's how you run it.
There's gotta be a way.
Oh god. But anyway, that's how you would run it. You would compile it and then you would run the build once it compiled. And you can see that I made an oopsie in some of the code and I had to fix it. It's fine. Don't worry about it. But yeah, next up are your imperative languages. That's the next category that we're looking at. And if there are any questions, let me know. If there's a question in the Jitsi, just yell and I'll look. But yeah, imperative languages are kind of the opposite of the declarative languages. These are the languages where you tell the computer how you want to do the thing, and you make explicit changes to the environment as a whole rather than the computer doing all that. So that's a meme that I think pretty well describes the difference between the two. Imperative programming is this is how I give you money, and declaratives just take my money. So one of the first steps is procedural programming languages. They're based on procedure calls, which is kind of like the functions that you would see in functional programming. Essentially, it's just a series of steps that can carried out, and these blocks can be called around during any point during execution, and you can control the control flow. So your if statements, your while loops, your for loops, they're all there, and it's very procedural, so they go step by step down the line of the code. Prime example of procedural programming language is good old C. C is statically typed, and it is used in many tools like OS kernels and tools like Vim and Git. It was first created around 1972. It's known as the mother of all languages just because of how many other more recent programming languages were based off of C, and it is a compiled language in and of itself. So here is an example of a factorial written in C. You can see the function using the for loops. We've missed them. And you can just see it hard coding and printing out the factorial of a function. And this would be the procedure that it would be talking about. So here's how you'd run it. I didn't show the steps for compiling, but it looks fairly similar to how you would compile the Haskell code. So yeah. Yay. Next are object-oriented programming languages. They're sort of derived off of procedural languages. They were made as a sort of way to make procedural programming more friendly with data and just to better handle data. And because of that, they break things down differently. Instead of the procedures, they're broken into objects, and they're seen as a way to better break down problems into the real world. The best way I can describe it is procedural languages will break things down into verbs like write, get, set. Object-oriented languages will break things up into like nouns, like dog, cat, book, stuff like that. And then there will be data and methods, which are like the procedures, attached to those nouns or those objects. And because of that, they also have the access modifiers, which is your public, private, and protected words that you'll sometimes see before variables, which is essentially saying, deciding what parts of the program can access certain parts of data. And object-oriented languages also allow for a lot of reusability. This is like the most common way to explain object-oriented programming is you'll have a class called student, and then your objects will be instances of that class. So Adam and Kesha, they will all have the data that a student class would have. An example of this one is good old Java, because Java forces you to be object-oriented. It's not like C++ where you get the choice. Java forces you. And fun fact, I was gonna use C# instead of Java, but C# doesn't play well with Linux, so we went with Java instead. But yeah, Java is compiled and kind of interpreted because of the way the JVM works, and it's made to be write once, run everywhere. It's made to make it so that it's a compiled language, but it's not platform dependent. It was first designed around 1990. It's used on the, I'm pretty sure I spelled that wrong, but it's one of the Mars rovers, and it has a built-in garbage collection like Haskell. So, what?
It's finally starts cutting out space.
There we go. So there is an example of a factorial in Java. You can see the class factorial because you don't get a choice in that. And then the function that allows you to loop and calculate the factorial of 5. And you would run it. I also didn't include the compile command for this either, but you would have to compile it and then execute it like that. The main function's right there, public static void main.
Oh, right.
There you go.
I hate Java.
I don't know what you're talking about. Java's the best. Java is amazing.
I don't really see the problem with Java. Like,
Java's on over 3 billion devices.
Exactly.
And-
Most of them are running Minecraft, probably.
The next way you can describe our programming languages is how those languages are run. This section is going to be very broad. I'm not going to go far too in-depth into it because Jeremy here is actually going to be going much more in-depth in these type of stuff next week. So this is going to be more of a broad overview of this is sort of what it means when you hear this word. Cool? Cool. Please don't ask me. I won't be able to answer any questions about any more in-depth.
Basically, it's next time on Dragon Ball Sad.
Honestly, yeah. So what does it say when a language is compiled? It means the code is translated into machine code before executing it on the computer. That's supposed to say computer, not compiler. Actually, no, wait, I just read it wrong. Never mind, I can't read. It's fine. So yeah, essentially translated into machine code before translated by a compiler before it runs on the computer. Think of it as you have a book written entirely in French. Someone will take that book, translate it all for you, and then give it to you so you can use it and read it. It's fast because it's executed directly on the CPU, but the cons is that it can take a while to compile the code, especially if it's really long. And there's also that platform dependence because you're translating it straight up into machine code. An example of a compiled language is Rust. Yay, I refused to duplicate languages in this presentation. That's why there's so many, and that's why I was stressed. But yeah, Rust. You can use a lot, it's used a lot in game engines, databases, and operating systems. And it's the third language to be added to the Linux kernel after C and assembly. It is an imperative compiled language. It is memory safe, meaning that immutable variables are by default, and they have this sort of function called ownership and borrowing by the Rust borrow checker. I'm not quite sure how that works because it does get a bit complicated and out of the scope of this presentation. But if you wanted to look more into it, I'd highly recommend it. And I also learned this, apparently. Fans of Rust are called Rustaceans, and I think that's amazing. That is the greatest thing I've ever heard.
I think Nicola might be a Rust.
Is Nicola a Rustacean?
Absolutely.
I'm not
it's
surprised.
phenomenal.
It's phenomenal.
You should
No,
have
I'm a LARPer.
you should have had the meme where the guys at the party is like, "Hey guys, did you know Rust is memory safe?" Everyone's like, "Yeah, you won't shut up about it."
The intro one.
But yeah. Come on.
Oh yeah, that
You
was
can do it. There we go.
Yeah.
So here's an example of a program run in Rust. As you can see, it does look closer to, it is an imperative language, so it does look closer to C and like C++ or Java, not Java. Anyway, so it does sort of look like that. Fairly similar. And this is what it looks like. That's how you would compile the program, and then you would run it similarly to how you would run the C file or the Haskell file.
Why is there an exclamation point in the function call?
Don't worry about it.
It's just very safe.
Oh yeah, this also wasn't written. This was also written by my friend Drew. So yeah, that was one of the ones I had to like offhand because I just didn't have time to learn Rust. But yeah, that's Rust, and honestly, the compiler is kind of nice. So I would recommend, I would learn Rust on my own time. Next up are the interpreted languages. Instead of a compiler, they have an interpreter. Essentially, they go through line by line and execute the code itself instead of directly handing it off to the machine. The best way that I could describe it, and this one is I don't know how well this example goes, but say you have that same book in French, but instead of someone translating the whole thing and then giving it to you, they just translate it line by line as you read each sentence. And that's sort of how interpreted languages works. It's great because there's no platform dependence, because the interpreter's executing everything, not necessarily the machine itself. The cons, though, is that you won't see any bugs until runtime, where compiled languages, because you're doing that build stuff first, you'll see the errors then. So you won't see any bugs until then, and then you will always need to have the source code. Again, with the compiled languages, you build it into something else, and then that's what you execute. With interpreted files, you need to keep that source code there because the interpreter needs that in order to run and execute the program.
When there are bugs, they're generally more helpful in interpreted languages since you have like more information available to you as the person running the program.
Okay.
Because in compiled languages, you'll just get segfault, just crash, and you have to get out of debugger and like, I'll go over this in my presentation.
Unless it's Rust. Rust is pretty nice, huh?
What is SIO?
It's probably a typo.
Okay.
That was probably supposed to say, that was probably supposed to be something else. Like I said, I was rushing to finish this part of it. So sorry about that. But like I said, because you don't have that build beforehand and it's going line by line and all that fun stuff like the book, you can understand interpreted languages tend to run a bit slower. An example that I use for interpreted languages, Ruby. Y'all thought I was going to use Python. Ha! We use Ruby. It first appeared in 1993. It's an object-oriented language, funnily enough. Everything is an object and can be modified. Scary. And it's also dynamically typed like Python, so you don't need to specify that something is an integer. Ruby will just figure it out on its own. And it's used to create stuff like Twitter, GitHub, and Airbnb, apparently. And it relies a lot on regular English words, so it's like a fairly high-level language in that definition. So here's the example I used for Ruby. That's what calculating a factorial looks like in Ruby and then printing it out.
Whoa,
It's fun, right?
Wait, what is puts? Is that
Puts
like
is
print?
printing it out to the terminal.
string.
Put string.
Oh, okay, I get it.
And then that is how you would run it in the interpreter. So there's the file, it's a .rb extension, and then you just do Ruby and then the name of the file and it'll run it.
It's just bash.
It honestly is, it's honestly kind of nice. I really like it. And you're right, it does look like Bash.
You kind of slept on question.
I hate interpreted
You agree
languages.
it's clear in this? Or you want?
Except MATLAB, that's.
I said used, and I didn't say it was all written in it. But yeah, so really with, you only really get two options with the language. It's either compiled or interpreted, and there's, as you can see, there's a lot of pros and cons with each of them.
Oh.
I'm so sad the audio didn't play. But no, yeah, just-in-time compiled languages. They are lazy compilers, which means they're only going to compile what they need. So, for example, say, kind of like with Haskell, say I have two functions. Craig's making a face. I think he knows where this might be going.
No, I don't.
Okay. But say we have two functions and Julia only uses one of them. It's only going to compile the segment of code that it uses and not something else. The Java virtual machine actually works like this, where it will only compile, it will selectively compile the stuff it needs to help make things run faster. And so it's essentially a better way to get better performance than interpreters without having all the cons of a compiled language. But the con of just-in-time compiled languages is that it's going to be hard to, it's going to take a bit to run its first time because it has to compile everything. But after it compiles everything once you run it again, it's going to be faster because of that. Because it's already going to have the stuff that it already looked at built and ready to go. So here's an example of the factorial in Julia. And it doesn't look, it kind of looks a lot like Ruby. It was first developed in 2012, dynamically typed, like Ruby and Python. It's functional. Everything is a function. I ranted about this a lot when I did my Julia talk last semester. But yeah, everything's a function, even the math operators. You can write the math operators as a function, and Julia will be like, yeah, this is fine. It's commonly used in mathematical computing, data visualization, and machine learning, and it also runs natively on a GPU, which is pretty cool if I honestly say that. As much qualms as I have with Julia, I think that's pretty neat. And that's how you'd run a Julia file. It looks a lot like the Ruby file. So we're gonna compare compiled versus interpreted languages now. Just sort of see what the difference is as the programmer when you're running things. Our baseline is going to be assembly. Thank you, Henry, for writing the assembly for me. So that's how you calculate a factorial of 5 in assembly. Specifically, x86.
It's not bad.
It's-
313 verse.
That 313. That's nothing.
So it first appeared in 1947. It's a low-level procedural compiled or assembled programming language. It's essentially made to help simplify CPU instructions. So it's actually considered a high-level language because you're not dealing with straight-up assembly code to try to run the instructions from the CPU. The thing was that there's a lot of different, I saw the word flavors, I don't know if that's right, but different flavors of assembly because each processor has its own instruction set and therefore a different type of assembly to run it. This is going to be Intel. I have an Intel chip on this machine, so it's going to be using x86 assembly.
Which flavor x86?
Is it x86 64?
If it's 32-bit, I'd be worried.
Yeah, it's 64.
Must be 64.
I
It's
would be
64.
worried. 32-bit Mac.
don't know, ask the person who wrote it.
NVX 512.
Anyway, x86 assembly, Intel chip, yay! So the first comparison we're going to do is readability. So up here we have Rust in the top left, my left corner here. Assembly is over here on the right, and over here we have Ruby, and over here we have Julia. So as you can see, in terms of reading, Julia and Ruby definitely are a bit easier to read as someone who isn't used to programming languages before.
The assembly is the easiest one to read. It's the only one that's commented.
No, that's valid, but in terms of
Otherwise,
the,
no one would simply to understand anything.
yeah, we all love clean code here. Anyway, so neither of you were looking. Anyway. So as you can see, then Rust sort of sits in the middle of the two, where it's not as hard to read as assembly, but it's not as easy to read as Rust or Ruby or Julia. Next up is speed, because we all care about how fast it takes the program to run, right? Ha ha! Julia's a bad example of just-in-time compiled languages, guys. It did worse than everything, by a lot.
Weeping Bell Pog.
And then but as you can see, assembly is obviously the fastest, and then it then goes to Rust, which is a compiled language, and then it's Ruby, which is interpreted. So you can see the difference in these examples of compiled versus interpreted and assembly. Just ignore Julia. Just ignore it. It's fine. It's not fine, but it's fine. But yeah. So that's about all that I had there, but we're gonna have some closing remarks real quick about it. So the TLDR, there's a lot of ways to classify languages, as you could probably see from this presentation, they're not mutually exclusive at all in the slightest, which makes things really annoying and really hard when you see these buzzwords. But you probably won't have to worry about it too much, except for the difference between an interpreted and compiled language. You should probably know that, but all the others you could probably get away with not really knowing, except for maybe object-oriented, because that's a buzzword. Definitely the difference between interpreted and compiled languages for sure, and as I said earlier, Jeremy will be going much more in depth on the difference between those two next week. But it is also kind of fun to look at a language and try to figure out by its structure what it could be, especially since you start noticing patterns once you realize what a language could fall underneath. It's honestly really neat. So first up is R. Thank you, Patrick, for writing the R program for me. Here's the calculation for factorial in R. As you can see, it is an interpreted language, and it is primarily used for statistical computing. It is an imperative language, and you can kind of see that because you're not telling R what to do, you're telling it how to do that. I'm not saying calculate factorial, I'm saying do it this way specifically. and it has both procedural and object-oriented capabilities. I didn't know that. I didn't need to know that. I didn't need to know that parts of R were object-oriented. And it also has first-class functions like Julia and Haskell. Next language, BrainFEC, because we're gonna keep things nice in this presentation.
And in the meme.
You put it in the meme.
You know what? It's fine. I didn't say it, so it's okay. But yeah, it's Turing complete, which I didn't know. I didn't need to know that it was Turing complete, but it explains a lot. And it wasn't really intended to make software. It was more so just sort of like, haha, look at this fun language that really has would be really hard to use outside of just being fun. It is a compiled language, and it was developed, I think, originally in 1993. What you're seeing there is a Haskell script for Hello World, because I couldn't be bothered to try and do factorial in this language. But believe me, I tried.
Oh.
I did try, and I failed. And then there's emoji code. Emoji code is a compiled language. Almost all the symbols are emoji, and I'm convinced that it's just C++, because you not only need the C++ compiler, but if you squint really closely at that segment of code, kind of looks like it, doesn't it? Where the C out is the smiley face, your quotation marks are the ABC, and then you have the arrow, which works as the star end line. And then you have the int main is your because the checkered flag is how you start a program. So after the checkered flag is how the compiler knows that is code to be executed. And then you start a block of code with a grape and you end it with a watermelon. So when you think about it, the grape is the opening bracket and the watermelon is the closed bracket, and then the checkered flag is int main.
Wait,
Do you
so
just
if-
not get arg values then?
Now,
Wait, hold on. So
Basically.
if this is C++,
I'm
where is the
convinced
return
it's C++.
zero?
You don't need it. It'll be fine.
Probably found the one used for the Windows emoji keyboard.
Yeah.
But no, yeah, I'm legitimately convinced that emoji code is just C++, just all the symbols are replaced with emojis. And it gets worse than this. This is just hey. But so I put the link there if you wanted to learn all about the joy of emoji code. And I would have tried to calculate the factorial in emoji code, but I was not about to try and set up the environment to run emoji code on my computer. I wasn't about to try that. I didn't care if it needed this G++ compiler. I tried to do it in Code Academy, but Code Academy won't, in their coding playground, doesn't do emoji code. It was quite unfortunate. Made me really sad. I was like, oh damn, I can't do it. But yeah, that's about the end of things. There's my little ending memes there.
That's about it. Let's see it.
But honestly, that's all I had today. Were there any questions or anything about what I said today? I think I went kind of fast.
Hi, funny watermark.
I just went onto Google Images, looked up programming memes, and that was one of the ones that came up, and I thought it was funny.
Alright, so that's it.
Funny.
No, that's it.
Oh, that's fun.
No, you know, I thought I did put it. Oh, Discord wouldn't let. Discord was having a stroke with the meme that was sent earlier, so I couldn't actually get it.
Damn. What a shame.
Thank you.
Yes. Thank you, everybody. Join us next week for Jeremy's talk on, what's the name of it again? It's a continuation
compiled
of
versus
this.
interpreted.
Compiled versus interpreted languages. So if you liked what you saw here, we're diving deeper in next week.
Deep dive.
Deeper dive.
Deeper diving. You know
The guy in his
how we
computer
do
in the
it.
pool.
Alright.
Yeah, thanks everyone for showing up virtually too.
Thanks, everybody. We'll see you next time.